But we're back. Likelihoods. Questions. Do you have any questions for me? So, the process is this, right? We assume something about the data or the model, right? In a regression model, we're actually not assuming it about the data, although we say y is equal to this. We're assuming things about error, right? Right, that's usually where we make our assumption is error. But implicitly, that makes an assumption about y that allows us to move forward and do statistics with it. So even if it doesn't, you don't feel like we're making assumptions about the data, it's there in the background. So you have for any one person what the model is and what the distribution is. And then you assume, if you're assuming that your people are independent, you take each person's version of that distribution. And the only thing that differs between the two is each person's data, right? You've got a data, this x, yeah, there we go. This one, each person's x that you'd plug in for the data. So each person's function may give you a different height when you give a mean. So you're like, oh, here's a mean of 10, right? Not everybody's data like the mean of 10. Each one gives it a different height. So our process is literally to find values of mu and sigma squared that maximize this joint likelihood function. All right, so you take one person's data, you make the assumption that people are independent, and you multiply them together, and now all of a sudden you have the function that you use maximum. You have to maximize, right? That is you want the maximum of the likelihood function for any x for anything you don't know. That's it. Couple side notes, sidebars again. What if your people aren't independent? What's that? What do you mean by that? Not independent? Let's imagine like you have that you have data from people who are nested in classroom, or better yet, data from the same person over time. Whoa! If they're not independent, we really can't be doing this multiplication business. So we end up having to do something else, and that's where you end up saying multi-level and so forth. And really, what that does is it says each person's data is kind of multivariate normal. And then once you get past that, or each classroom's data is, whatever the highest level of unit is, that's where the multivariate normal starts. And then if you have multiple classrooms, then that's where the multiplication happens. So it's interesting. This likelihood for a person or for a unit for an observation can be almost anything. Right? It doesn't have to be normal. It can be any other distribution. It can even be another multivariate distribution. But that's where the flexibility comes in. So what I'm trying to express here is in this functional form with the likelihood at the top, we're doing things in multivariate normal land. We don't have to. We can do things with, Bernoulli's. We can do things with, ever heard of the Poisson distribution before? How many of you think of, my daughter used to like Little Mermaid? It makes me think of a song there. Anyway. Nobody? No? Yeah? Okay, at least one person, yeah. Thanks. I won't sing it. I'll really kill class if I start singing. But, okay. So do you get the big picture? Make an assumption about how a person works for their data. Get a sample. That assumption applies to all the people in the sample. They're independent. And then you get this likelihood function. In that likelihood function, we have to plug in values of the things we don't know. Mu and sigma squared. Those are our parameters. Once we figure those out, once we plug those in, we can get a height. So the next question is, how the heck do we figure out what those numbers are? Right. Well, one way that we can do it, actually I'll show you with a, let me get back here. So anyway, let me go over to my slides. I think my slides are a little bit out of order that I didn't catch. But if I go over to my R output, one thing I did was take our data. You're going to see this next. And try to figure out what the mean and variance, or the mean for each thing happened to be with it. Yeah, this is disappointing. I'm really sorry about that. This is the part where I cut out slides to show you how this works for one dimension. I can show you in multiple dimensions, and I will show you in just a bit. But let's pretend, right? How would we do this in a very naive way? What we can do is make a grid. Maybe this is mu right here. Right, this is the mean. This is sigma squared. And these are all the possible values that we might want to pick for each of these. Right? So let's imagine, if you're like me, you're like, oh, let's see where the mean is. I think it was 100. Let's start at like 95 and go up to 105, maybe in like 1 point increments. 4, 5, 6, 7, 8, 9, 10. There, 10, right? So this is like all the values of mu that I might plug in and try for the mean. And for sigma squared, maybe I can go from, I think it was 189, so maybe I'd go from like 170 to 230 or something like that and try out values. And for every combination of these, here's my mean and here's my variance, I take those, I plug them into that ugly formula and compute a height. Right? And do that again for all of these. Grid search is what this is called. It's a search. Ultimately, when we have a function like this multivariate normal, there's no one, well, back up here. What we're really after is the maximum of it for each parameter. What is the value of that parameter that maximizes it? In our simple case here with one, this is not simple, but one variable case, relatively limited case, we can actually use calculus to figure out what the maximum is. I don't want this to be a calculus class, but if you remember, if those of you who took calculus, the maximum of a function, right, let's imagine this is our function right here. The maximum is right here, and we can figure out a maximum if we were to take a line tangent to it, and it was flat, right? It had no slope to it. Right? Actually, it's either a maximum or a minimum, and we could test which one it was, but this distribution is actually guaranteed. It's a what's that? Convex. Convex. Concave is this way. Convex. It's a convex function with one peak. Right. This one down to the top of it. So the derivative, if this was the mean, right here, the derivative of that thing with respect to mu, if we set it equal to 0, we could solve for it and find it and so forth through calculus. That sounds really complicated. Same thing with the variance. Believe it or not, if you did that, and you can do that, I would advise you to take the log first. Okay? The mean, can you imagine what the mean would be? There is actually a closed form for it. It's the sum of x across all people over n. The mean that we would believe it would be, right? Pretty awesome. Yeah, I thought so. Excuse me, sorry. I have my phone on in class because just in case I have to rush my wife to the hospital to give birth to a baby, and that's a number that I don't recognize. So, apologize. I'm like, am I springing into action? I told the child before I left today, don't you dare. Today is not a good day. You're not allowed to be born today. That's right. So, thankfully, that's a false alarm. Okay. My apologies to have my phone on in class. Normally I'm not that way, but I feel like I'm on call, you know? Although I sort of tried to better this weekend that I let her pick the over-under of when she'll deliver. I was like, would you want to, you pick the date and then tell me if you'll be before it or after it, and I'll get the other one, and the loser has to drive themselves to the hospital. She didn't want to take that bet. But anyway, she thinks she's going to be done this month sometime. Her due date, March 13th. We'll see what happens. But anyway, thank you for your understanding. I apologize to be kind of on the edge. But, you know, she's not going to Lawrence. She's going to the one in Overland Park. So it's the place. It's that distance that has me on edge, a little bit nervous. That'll be fun today. Oh, man, I need to borrow that truck. But I don't know what's more fun, talking about rushing to the hospital while in labor, or derivatives, labor or delivery, either one. Maybe, and believe it or not, I kid you not, whenever we went to the childbirth class and they're trying to this is her first time going through the process, and she, they're like, well, here's what labor is like, stages of labor and whatnot, and they're like, well, you need a focal point and whatnot, and so they have this exercise where she had to hold on to ice, like it would hurt for a minute, and her goal, it sounds really like torture, but it was really just to try to focus on something outside of where the pain is, and believe me, it's an experience I'll never know as a man, but I get it, it's going to be really tough. And so as she did that, I was trying to talk to her about estimators. And it worked really well. And she said, so mind you, this is related. Labor estimation and like where life begins, right here. This is, so if you were to do calculus with the mean, it would be this. Can you guess what the variance formula would be if you did calculus to find it? Sum of p equals 1 of xp minus u squared all over n. That is the maximum likelihood estimate of the variance. And remember, the square root with n versus n minus 1, bias versus not, right? Maximum likelihood has an n at the bottom. So that's where it comes from, literally. But most of the time, we're not so lucky to have these closed forms. When we do structural equation modeling, we're not just going for a mean and a variance. We've got this covariance matrix, and we've got all these other terms floating around. And better yet, the mean is a function of some things, the variances are a function of other things, and so we can't just come up with a formula and get a result. So what we end up having to do in maximum likelihood is to come up with a better way of searching, right? We could use a grid search here, but that would take forever, even for small problems. But a better way of searching, we call these efficient methods. If you have this distribution, the way I like to think about it is, and we've got the hill here on campus. If I asked you, if I drove you somewhere and blindfolded you and drove you somewhere, that sounds very sinister. And I let you off and say you're supposed to find the peak of Mount Overyek. I know it's now. The mountain here in eastern Kansas. How would you go with blindfolds on? How would you figure out where the peak was? You search around, figure out where the hill was going up, and you take a direct step in that direction, right? And that's what maximum likelihood estimators do. They basically start somewhere. They get a random starting point. They take a guess. Here's your first mu guess, right here. And using calculus, we can figure out where the slope is going up. We want it to go up, right? So we could figure out a slope to it, and then we can take a better guess. And we can keep doing that process. And that process goes by a name. One of the words, there's several versions of it. One of them is something called Newton-Raphson. It's a method for finding the peak. Once it gets up to the top, you can't keep going, right? When you're on the peak, when you're on the top of the mountain, every direction it should be down from you. The slope is down. So you know you're at the top, you stop. That process, every step is called an iteration. So every step, you get closer and closer to the peak. It may take you a long, long time to get to the peak, but every step you get closer. At the peak, once you stop, you'll have an estimate, right? For each of the parameters in the model, each of those estimates have all those nice properties that ML uses. Asymptotic consistency, efficiency, normality, all those things are really good. But if you're not at the peak, like if you stop right here, if you get tired, like me, if you're hiking with me, we stop a lot. Maybe I teach a workshop in Boulder. I've gotten lucky to teach a workshop in Boulder the last 3 years. And I like to go up, over to the little side park that's not really the mountains, that the rookies still hike on, and I struggle on it. And we stop. But if you stop here, you don't get all the good properties that ML estimates do. A lot of times what you'll do with a program, it'll say it did not converge. That's not convergent. So your iterations get up to a point, and perhaps you run out of steps in the computer in R and LaVon. It gives you a default number of steps to take before, if it hasn't found the peak, it will eject and say, I can't find it. But in that case, it hasn't converged. Don't use those numbers. Not good. Those numbers don't give you all the guarantee. You can just go ahead and ask Templin. You might get better estimates. Okay. So, where do the standard errors come from? You thought you had enough calculus. Craig Ender's book, the chapter I gave you this week, did talk a little bit more about that. That likelihood function, right, the derivative of it is where the peak is, where the maximum is. That's the first derivative. But if we were to continue and take a second derivative with respect to that parameter, that term itself forms what the standard error for that parameter estimate. Remember, standard error is how much error there is in the estimate. We use it in the Wald test, right? We use it parameter divided by it to give a p-value for it. That term, for each parameter, the second derivative evaluated at it is -1 over that is the variance of that parameter. The square root of that is the standard error. It gets a little funky after a while, but remember this. Form the likelihood function. If you find the peak, it's just calculus to give you all the results that you need. Now, we don't want to do that calculus, and you don't need to do that calculus. Someone's done that before, but that's it. It's findable. And that, when you have all of the, like here we have 2 parameters, so that it's actually a matrix of standard errors. It's called an information matrix. It's not actually, the matrix of standard errors is not the information matrix, but it's -1 times the inverse of it, which is really crazy. But, so, let's do this with the maximum likelihood with multivariate normal. Do you have any questions for me? I'm kind of running out of space here. I don't want to make this too technical. Yes, Devane.
I know you said this before, but I guess it's just the same way of curiosity.
Yeah.
When it comes to these maximum likelihood estimates,
Mm-hmm.
the computer will either find the peak or it won't convert.
That's right.
It'll never, and I hesitate to use the word never, goof a bunch of times, thinking keep sliding a bunch of down tangent and say, I found the peak when the peak's really high.
That's a good question. It depends on which model you use and which program you use. If everything goes according to plan, the Newton-Raphson to find the peak will never go over it. Right? It'll always keep getting closer, but never go. And other versions where we're using Newton-Raphson, so if you're in an IRT model, for instance, we actually have to somehow take care of theta, take care of the latent variables before we do our maximum likelihood. That also will stop. And in our models, if you only have one peak, you'll find it. Bless you. But if you have a model where you have more than one peak, like what we call a local offset, so maybe it looks like kind of like a mountain range, right? You got one here, and then it looks like that. Wherever you start, you'll find the peak closest. You may not find the global. So there are cases where, in algorithms, where that may happen. More broadly, in terms of would it ever happen, where you normally see it happen is if someone's written a program and they've written it in a way that's not very good, it'll look like that's happening, but it should never happen. So that's your indicator that this program doesn't work. And so everything that we see in this class, we should never have that problem with. If LaVon is not written in a way that's stable, you might see that because of rounding error, actually, but it should never see it. Does that answer?
Yeah.
Other questions? So again, big picture. Assume something, get a likelihood function for a person. Across all the people, you get a likelihood, sample likelihood. Use that to find your parameters. Do calculus, find the standard errors. Cool? Cool. Let's do this with maximum likelihood. Remember the maximum likelihood with multivariate normal. We'll give you an example here with the data, the IQ data, and plug in numbers and actually do a grid search to show you the function it's finding. This is the multivariate normal. It's ugly, right? It's still normal because of 2 pi. This is it. What does it do again? If we have a person's data, but we don't just have one observation, we have a bunch of variables. Maybe this is 5 variables, right? This tells you how likely it is to observe all 5 all at once. So that's their data. It's this vector of observations. The mean, each variable's mean is in the mean vector. Think of all the statisticians who've made terrible puns about the mean vector. Like just waiting for you to talk about it. Lindsay Lohan and the mean vector. No? Mean Girls? Yeah? No? I've never seen that movie, actually. No, stop it. When the guy in the Texas Snuggie says stop, you better quit. No, so that's the mean vector. And then sigma is the covariance matrix, right? The diagonal is the variance for each of the variables. The off diagonal is the covariance. So, but again, you plug all that in and you still get one height. Right? It's just one height to find. And so the process still works the same way. There's all the variables that go into it. Here is a picture of it before. What we want to do, we can do the same thing with our data. This is just setting it up like we were last week. If we knew what the mean and the variance was, which we don't know, but if we did know this, we could plug in any pair of values for each person and see how likely they would happen to be, right? So here the mean is 100 for IQ, 10.35 for performance. You see the covariance matrix. If we saw a person whose value was an IQ of 100 and a mean of 10.35, their height would be 0.0052. Note, they're right at the mean vector. So they are at the peak. They're going to be the most likely value to have happened. Whereas somebody who has a value of 130 for IQ and a 13 for job performance would have a value of likelihood of 0.0004, which is they're less likely to happen. That's all there is to it in terms of the other way, in terms of plugging in numbers. How do we go about finding this if we wanted to flip this around and say, wait, we know the data, we have no idea the mean or the mean vector or the covariance matrix. Right? Same way. We'd have to build a sample likelihood function. Right? Here's where it gets a little bit more complicated. How many observations do we have per person in our sample here? 2. Right? So that each person, if we look at this, each person would be assumed to have those two values follow a multivariate normal distribution. So each person's little distribution would be that ugly multivariate normal distribution and its height. So we take the product of all those and we get this ugly, ugly multivariate normal distribution. It even gets uglier. Derivative or determinants and inverses and exponents and all that stuff. But that's what we use. Now, if you wanted to figure out what the values of the mean vector were or the values of the covariance matrix, how many unknown values would you have in total here? How many means? 2. How many variances? 2 variances. 1 covariance. We have 5 total parameters. So our maximum likelihood algorithm won't be as easy as drawing it in 2 dimensions. We have 5 to search over. Right? So it gets a little bit more complicated, but the computer can search it over and find those 5 values that produce the peak given our data. And sure enough, they should be equal to what we just observed in our hand calculation of the variances and covariances. So we're going to do that. A lot of times, so this is the likelihood function itself. Right, this is just the normal distribution, the product of all of it across. And that's what how you read this. Capital L is likelihood, X is your data. The likelihood of the data given the parameters. Right? That's this thing. A lot of times we just call this L. But it's really hard to work with because we have so many exponents and so forth, particularly if we're using calculus. So a lot of times we take the log of the likelihood. And what this really is the natural log. So we take that distribution function and just put it in the log function. And if you remember how logs work, a log of something to a power, right, it became that power times the log of that thing. You take the power and make it's multiplicative. Right, so you bring down the exponents. And then we bring down this exponent, and the log, or the natural log of this E number, Euler's constant, is 1. Right? They're inverses of each other. So that goes away. So this is what we end up trying to maximize. Pretty ugly. But let's do that. Here is the R syntax that produced it. What I did in this syntax was to say, I know, let's just pretend we know the covariance matrix. I wanted to produce a kind of an MLE, a plot of that likelihood, log likelihood function with something we could see. So I took 2 dimensions. I just took the means. I said, I don't know the mean of IQ. I don't know the mean of job performance. I'm going to guess around for those. But let's imagine I know all the variances, all the covariances. So I know sigma, and I know the data. So now all I need to do is plug in each value, a pair of means, and I'll get a height. that's what I'm doing in R here. And believe it or not, there is a function in R called DM norm. D is for distribution, M is multivariate, norm is normal. Right? This is what you'll use in your homework. That way. You give it your data. Sometimes you may have to put the transpose function in. Right here, this is the transpose of my data. You give it the mean vector. You give it the covariance matrix.
So the T here represents for what?
Pardon me?
The T here represents for what?
Yeah, that represents, I have my data as a a column vector. So the way I entered X looks like this. And really what the function wanted it to be, T of X is its transpose, right? Which would be the row vector version of it. Like that. And this is that, when I was teaching you matrix algebra last week, I said the transpose exists because sometimes we have to get the shapes to work out. Each of these functions, I think there's another function that someone wrote in R that doesn't want the transpose. So it's just, we're just reorganizing our data to make it work with the function that works. So these are the values from the previous example I just plugged in. If I were to search through it, right, these are the values of the likelihoods. One other thing that you can do in this function, you can add after covmat a comma and put the word log equals true, and it will give you the log likelihood of that function, not just the likelihood. Right? So that's very helpful. So our function is the following. We want to do this right here. For any given person, though, the log likelihood, if we go back in time a little bit, remember our likelihood function right here with the product of all the likelihoods? If we take the log of that, right, if we call this capital L, the log likelihood, log L, would be equal to the log of f of x1 plus the log of f of x2, all the way down to the last value. Log of f of xn. Right? So, why am I saying this? If you can think about it, what the log likelihood makes it possible to do is to take that function for each person, say, oh, I'm going to try out a mean of, this value, a mean for the first variable, this variable value, and the second variable, this other value. You have the two unknowns you don't know for your function, you plug them in, you get the log of that for the first person. All right? You go to the next person, you have their data, you plug their data in, you get the log of that, you add it to what you had from the first one. And you just keep adding up the log likelihood. So each person is adding a little bit more to your log likelihood. Each person's contributing a bit by bit. So each person separately is doing their part, if you want to think about it. All right, that's how this works for each person. So this is the function for it. This is the log likelihood function. And this is the sum of I try out values here of IQ, and I try out values here of performance. Right? And the values I'm trying out are going to range. I'm trying out values in between just plus or minus 1 around their mean. So I want to show you what the peak of the function looks like. I'm picking these at random, or just arbitrarily. I'm just trying to show you what the shape of this function looks like. So I'm trying out 10 values between 99.5 and 100.5 for the mean of IQ. We know the mean is 100, so we should know that the peak should be there. And values between 9.85 and 10.85 for performance. And again, the mean for performance was 10.35. Right? So if everything works the way we should see the maximum of this function happens to occur when we plug in 100 for mu1 and 10.35 for mu2. This loop down here, you don't need that for your homework. You don't need to do any loops at all for your homework. You may just have to sum things together, and I'll talk about that in just a bit when we get to the end of class today. But this is what it's doing. It literally is adding, for each, we have 20 people in our sample. We take this log likelihood, which is given to us by DM norm, and add it to the sum, the sample. So it's adding it. So what it's doing is it's plugging in one value from U1, one value from U2, and then checking out what the likelihood is for each person's data, or log likelihood is for each person's data, and adding those 20 numbers together. And that's what happens in the computer when we do our estimation as well, right? Even though it's called Newton-Raphson or whatever else, what it boils down to is you get a guess as to what the parameters should be. It shows up in a multivariate normal likelihood somewhere, and then you try that likelihood out on everybody's data. Right? And the value of those things that you plugged in to the likelihood that give you the biggest, the highest point at the peak, those are your MLEs. Those are your maximum likelihood estimates. That sounds very convoluted. Are you understanding it? I'm doing it for whatever reason. I'm feeling like I'm really struggling getting my point across. This one, I was feeling really good last hour, and all of a sudden now I'm Spike. I'm not Snoopy. All right? What can I do to help? Questions? Well, let's take a look at what we got. This gave us. I like the three-dimensional plot here. But in this plot, these are all the values that we tried out for the mean of IQ, right? It was from 99.5 to 100.5 in 0.1 increments. These are all the values of performance. And then the height of this thing, the third dimension, is the log likelihood that came back after we plugged in all 20 people's data into DM norm. Right? And so the shape that you see here, all these little points, are the combination of the first value of mean for IQ that we tried with the other value of performance that we tried. So there's 100 different points in this grid, right? And somewhere in the middle here is the peak. Okay? It's hard to see, it's very flat. Right? This is the idea of why is it so flat? We don't have a lot of observations. We have a lot of variability. Right? And if you're in the Ender chapter that I signed this week, variability around the peak, a very flat surface means there's a lot of error to it. A very peak surface has a very little error, and that's where that second derivative would come in handy. It would tell us how much curvature there was at the peak. So that's one of our reasons why it's very flat here. But this is the log likelihood, and this is the process, that process right there, those points, is analogous to the process that LaVon uses when it finds our structural equation model estimates. It may not be as simple as just saying, I want the mean of this, or I want the variance of that, but what it boils down to is somehow, in some way, it uses a function like DM norm with all the C people in your sample, and it tries to figure out the place where it has to stop at the peak. I think that's cool, personally. It took me years to figure this out. Like when I was in grad school, it took me forever. They didn't have this taught. I wish this would have been taught first. And if they ever, you don't want me to do this, but if they ever let me teach like the first year stat class, like your regression class, you know what's coming. I pity those people. But no, I feel like if you get this early, because it's used so much, all the stuff that you see from it will keep showing up over and over and over and over again. So, questions? It's fine.
There's like negative correlation between the IQ and the performance. So it could be changed like negatively.
It would the likelihood function itself would be in a different shape, but it'd be harder to say. So this is a likelihood function. The distribution, if there was, the distribution of the data would look different. But this is not just the data. This is the distribution of like the mean, or the variance, or the parameters. And so you would have to try it'd be a negative value up here. Not the height. The height itself, well, I guess the height is negative. The log of a number between 0 and 1 is a negative number, so that's where it shows up. Other questions? All right, let me see if I can try to recover from being Spike. Okay, most likelihood functions have to use that iterative process to find their results. Right? So you'll find these things, these algorithms. I want to show in just a second. We're going to switch over to LaVon I'm going to show you where it says algorithm converged. Those are like, if you see those numbers, awesome. And I just described to you how iterative algorithms work. They start somewhere and they search around for the peak. And usually they get really good answers. In practical terms, we talk about derivatives and all this stuff, calculus. It sounds really complicated. What a likelihood will do is they'll say, here is my log likelihood at one iteration. So it may be like this dot right here. This intersection right here between those lines, that is a log likelihood at one iteration. Let's say the next iteration was this one. It'll say, oh, look at that. It's higher. Oh, I'm going to keep going. Right? It'll do it again. Oh, it's still higher. I'm going to keep going. It'll do it again. Oh, it's higher, but not so much higher. And then it'll do one last time. Oh, I'm not high enough to keep going. It's effectively 0. So it's really a subtract. It's like, how much closer are you to the peak this time than you were last time? So you see really small differences. And so where it stops is something called a convergence criterion. It's an arbitrary number that you pick to say, what's the difference between last iteration's log likelihood and this iteration's log likelihood, to say that's effectively 0.
Is there a default?
Always a default, but the default changes by program. In LaVon, I don't know what it is, although I can look it up when we get to that part of the class. It's usually something like, I want to say 10 to the negative 5 or negative 7, so it's a very small decimal value between. The more technical programs, or the programs that tend to be written by bigger companies, SAS, for instance. SAS is a very large company of programmers and statisticians. They have not just one criterion, it'll have to satisfy 2 or 3. So it'll have to be an absolute difference and a relative difference, and so terms that to make sure that you're at the peak, because the peak is so important. If you don't get there, you don't get the properties you want. Okay. Another side note about the peak. When I started here on campus, I had a colleague in my program. All right, so that's narrowing down who the list of these people could be. This person said, sometimes when the model doesn't converge, the results just make more sense. Right? That is that's not even scientific. That is bad. Right? This is a person who taught courses in statistics. So, peak is important. This is a person who could have used a lecture on maximum likelihood to help. But, the calculus, I don't need you to learn. I don't want you to learn it. It's not important. Learn how to use it, though. Don't use a non-convergent result. The funny thing is, when you run in LaVon, and I broke this rule because I had just started using LaVon to teach this class because I wanted to make it something free for you to use. And I started looking, and I didn't, at first, look to see if convergence had been achieved. And sure enough, I started interpreting results that hadn't been converged. So always, when I built this lecture, I was like, oh, I made a mistake in syntax. So anyway. So not only, so maximum likelihood comes in more than one flavor. There's always a modifier to it. One that you'll hear a lot of in statistics, something called marginal maximum likelihood. That's for variables that that have latent variables that can't be, where we can't get them out of the likelihood function, right? So if you have like a factor for somebody, the factor better not be in the likelihood function itself, because that will cause a problem with the asymptotics. Every time you add a person, like you want n to go to infinity, you keep adding a parameter, like a factor score. So that's where we come up with something called marginal maximum likelihood. We use calculus to integrate out the factor, the things that we don't observe, and then we maximize what's left. Methods that use this, multi-level models with not normal assumptions. Item response models use it. SEM if you have non-normal responses as well. So that is where you find that. Okay, let's go into LaVon real quick. LaVon's default. And you got to know a little bit about LaVon on the first homework. By the way, thank you all for working so hard on the first homework. I hope it was a decent introduction to LaVon and R. I realized the starter syntax that I put online didn't have the read.csv file, but somehow almost all of you got it in, so awesome. I need to do better about the starter syntax, so I need to double check my starter syntax for homework 2. Make a note. Anyway, but as you saw in homework number 1, the very first model was the weight variable and then double tilde the other weight variable again. Right? It was an odd syntax. What that triggered, what that piece of syntax literally meant was, I want to estimate the variance of weight. Right? The double tilde is something for variance or covariance. It shows up in the covariance matrix. But what LaVon did then was assume, oh, you told me nothing else about weight, but you want its variance. Okay, I'm going to assume it's multivariate normal, in this case one variable, so univariate normal. And because I have a mean to estimate too, I'll just go estimate it as well, just for the heck of it. And if you remember the model output from Model 1, you would have seen not just weight variance, but you'd also see weight's mean as well. Okay? So that is what LaVon does by default. It literally goes and say, okay, you're going to estimate a multivariate normal model for all the variables you tell me that are in it. Right? You can tell it otherwise, but that's its default. The more jargony terms for it is we use a mixed model, a linear mixed model to do this. But where this shows up, the type of model this happens to be, shows up in almost every part of multivariate statistics. Multivariate ANOVA, for instance, if you've taken multivariate or are in multivariate, you may see that actually can be done in LaVon. Repeated measures ANOVA, did you ever get to that in your linear models class? That's one of these things. Right? You can get the same results with LaVon for repeated measures that you could have gotten in SPSS with the repeated box. Factor analysis, confirmatory factor analysis models show up there. Structural equation models show up there. Path analysis. These models cover lots of things. Heck, when you get into it, we could do a longitudinal model in here, a multi-level model in here. There's all sorts of things that this class of model works, and what it, at its core is this multivariate normal distribution. So, later in the semester, we're actually going to work with distributions that have not multivariate normal, but for now, we're going to say multivariate normal land, because at least to try to solidify what it means. So, here is an example unconditional model. If I wanted to estimate the covariance between IQ and job performance, PERF-C is what I call that, for complete data in this data set, I could make model syntax that have the double tilde. Now, by LaVon's measure, that means that I'm actually I'm asking for, here, let me back this up. If I have IQ and performance, and I make this X, right? This is my data. If this is multivariate normal, what are the parameters I need to make it work? Right? The mean vector for this thing will look like this. The mean of IQ and the mean of performance. I'll just call it P to save some time. The covariance matrix, we just talked about this in the previous example, we'll have the sigma squared for IQ, which is the variance of IQ, the variance of performance, and then the covariance of IQ and performance. Right? So there are 5 unique terms here. 1, mean for IQ, 2, mean for performance, 3, variance for IQ, 4, variance for performance, and 5, covariance. But once we know this one covariance, we just plug it into the top part, right? It's the same. It's a symmetric matrix. So what that syntax did is it said to LaVon, I want to estimate that thing right there. That is its covariance. Okay? I want to estimate sigma IQ and performance, the covariance between the two. So LaVon, taking everything by default as a multivariate normal, said, oh wait, you want the covariance? I see you have 2 variables here. And if I were to build out this multivariate normal, I'm also not just going to give you the covariance, I'll throw in the other 4 parameters all at once. Because otherwise it couldn't evaluate the likelihood. It needs all those parameters to plug into the DM norm function to give it its log likelihood. Okay? Okay. Let's see here. So here's what happened. Look at the top line there. LaVon converged normally after 22 iterations. That means LaVon tried out 22 different configurations of these 5 numbers. Then went through all 20 people plugged in their data to the DM norm function, figured out the height, and figured out on the 22nd one it had met the convergence criterion. It was close enough to 0 difference from 21 that it could stop.
So this means like 22 until reach like the peak.
That's right, you're at the peak. If you go a 23rd, you won't get much further from 20. It's effectively 22. It should not go any further. Yes, the beam.
So if it's not converged, it can converge normally. What else?
I think that's the only two. It can run out of iterations, right? You could have a place where it might just blow up for some reason that's not non-convergent, like there's an error, a bug. That may happen. So, non-converged means usually I ran out of iterations. Converged normally means I didn't run out of iterations. I met that convergence criteria. And then the other stuff is usually some type of program error. Although, hopefully we don't see that. The estimator we have here is ML, maximum likelihood. That's positive. And so this is what happens. We want these 20 people. It tells us the number of observations. It helps us figure what happens. And here are all the estimates, right? It gave us the covariance of 19.5, the means of 110.35, and the variances itself right there. So this term, this model right here, is something called the saturated model. Have you heard that term? Have I used that term in this class? I may have. No. Sorry, I talk about saturated models so much that just I forget who I talk about them with. When you hear saturated, what do you think? When you're not in statistics? Now, I took a chemistry class, so I think, the part to which, like if you think of the atmosphere being saturated, that's when fog forms, right? I don't know what saturated means. You have enough parameters for all the spots. You're having one parameter for all the spots there, right? This is in opposition to if you said, well, I'm just going to assume that they're uncorrelated, so I'm just going to put 0 right there. That's no longer saturated because you have no parameter here for that spot. Okay? So this saturated model, believe it or not, every time you run your version of SEM, your specific model to answer your questions, in the background, LaVon is running an analogous saturated model for it. Because nothing can fit better than the saturated model. It has the most parameters, it is the best fitting of everything that you could have for this class of model. So LaVon says, well, let's see. Does your model fit as well as the saturated model? That's the question that has to come. That's where this is why I'm putting this here. The multivariate normal, the saturated model, is a parameter in all spots. It's like saying, yeah, I have all these data, and they're just multivariate normally distributed, but I can't say anything more than that. They're all correlated, but I don't have a model to say why they're correlated or how they're correlated, other than just they correlate together. The end. Okay. Questions? All right, let's take 10 minutes. Come back and get to the exciting finish of this class.